I stay within the boundaries. Right?
No problem, no problem. So we've got a couple questions we want to ask you.
Okay, sure.
All right, Quinn, fire away.
So, how do you explain a qubit to a layman?
Great question. So a qubit is the fundamental computational element of a quantum computer, much like a bit is to a classical computer or conventional systems. In a conventional system, a bit has two states, 0 or 1. In a quantum computer, qubits can be a 1 or a 0 or both.
Now, what about null?
And not null, but both. And what I mean by
either or both.
Or both. Now, the both, what I mean by that in quantum mechanics, we would call that superposition. To describe that from a layman's perspective, maybe you think about this from a physical perspective. Imagine the globe of the world. And think of the South Pole being 0 and the North Pole being 1, and being able to identify any point on the surface of that globe. That's the kind of informational capability that we have in a qubit.
Because
and that's
it can
why
achieve
it
the
makes it
superposition.
powerful. Exactly.
Okay. So basically what you're saying is because the quantum computer isn't processing in linear aspects of like a 1 and a 0, because it's operating in like a quantum aspect of 1 and a 0 in superposition, it's able to calculate things at a much higher rate because of the simultaneous ability, essentially.
Yeah, so what happens is, as a result of the quantum principle superposition, and then also another quantum principle called entanglement.
Okay.
And entanglement is the idea that one element within a quantum system can be influenced by another element in a quantum system, even though they're not connected. It sounds a little hokey pokey, but that's actually real.
Is that through the observer effect, of when you observe the experiment, it affects the experiment?
So the observer effect is different. The observer effect is actually the problem that quantum information is very fleeting. So for instance, when you look at a quantum bit, then you destroy the information.
So it's actually something you can see, a quantum bit? I mean, like you can't see a 1 or a 0 in a computer, I guess if it's displayed on the screen, but...
Right, you have to evaluate it somehow. So it's the information within it.
Uh-huh.
But let's go back to your question now in terms of understanding the power here.
Okay.
So qubits, every time you add a qubit to a quantum system, you double the power of that
It's
system.
compounding the power, basically.
Exactly.
You're doing a compound theory rather than an incremental theory.
Right, so you can think of this as I'm able to represent 2 to the n states by my qubits, where n is the number of qubits. So in a 50 qubit system, I'm talking about 2 to the 50th power. That's a really, really big number, right?
Yeah, it's huge.
In fact, that number is bigger than all our supercomputing capabilities today.
Okay.
So wait, let me ask you a quick question. That cylinder there, that's a qubit under here?
That cylinder has 50 qubits in it.
In it. So if we open that up, what would it look like? Does it look like a traditional computer chip?
Yeah, it looks like a traditional computer chip, but it's built out of superconducting devices. We call them superconducting transmons.
What type of materials is that made of? Because superconducting, so normally this thing
we
is
use
frozen.
Aluminum oxide materials. There's some details that I can't describe here now, but essentially that gives us the superconducting characteristics if we operated at the correct temperature. In this case, the temperature is 10 millikelvin, which is colder than anything else we know in the universe. That's what we operate this at.
What?
Absolute zero is 0 Kelvin, so this is very, very close.
Okay. Wow.
So you're almost at absolute zero freezing temperature, which like is super high conductive depending on the material you have in the container.
Right, right. We use those cold temperatures to be able to preserve the quantum information.
Now, what kind of coolant are you using to reach that temperature?
Great question. So we use liquid helium, which gets us to 4 Kelvin.
Yeah, so you're using very similar to what like a collider would use for its sensors, is using the helium.
Sure, yeah. And then we use isotropic processing to take energy out in successive stages until we get to.
So you're almost doing like a reduction. to reach the excessive cooling level.
Is that what
Correct.
all these like spindly looking wires are all about?
No, actually, those things are coax cables, and you see waveguides, and down below noise isolators. We talk to the qubits using microwave signals. So this is to be able to get the communications in and out of the qubits.
So are you using like an oscillating microwave signal to talk to the qubits?
Yeah, what we use is we talk using 5 gigahertz, and we separate our qubits each by a megahertz.
So it's almost like you're phoning the qubit.
Excuse me?
In a sense, it's almost like you're making a phone call to the qubit, in a sense.
There you go. Yep. There you go.
So there's not even actually anything connected. So basically, you're just providing power to the chip, and then basically making like a phone call into the qubit.
That's a good way to think of it.
Wow. Why does it look so strange? I mean, it doesn't look anything like a computer.
Yeah, that's a great question.
So then, just
wait.
real quick, sorry,
Okay, sorry,
I didn't
yeah.
want to finish mine. So then, as you interact with the qubit, does it display a certain type of intelligence?
Yeah, so first off, programming quantum computers is completely different than classical computers. So you have to learn what quantum mechanical
very influence-based.
characteristics you can take advantage of in quantum computers to be able to program it. So then you program in these types of terms, and then you realize the answers that come back from that.
So you're programming in like key phrase terms, logic basically, and then the computer returns it back.
Right.
That's cool, man. That's cool. Thank you. Yeah, that confirmed a lot of my research.
Well, and you can use it online. You can.
Well, so I don't know. Maybe you can correct me. So then, a lot of the computing you deal with is a lot more about the questions you ask than the code you write, essentially.
Well,
It's like a questioning where it's phrase-based, where it's like a different than an instruction set, like programming was in a linear world where you would instruct. I'm trying to just grasp the aspect of like programming this in a phrase-based environment.
it's not a. I wouldn't describe it as a phrase-based environment.
Okay.
I would describe it in terms of in classical computers we have basic logic functionalities such as ands and NOR gates and things like that, right?
Case switch, yeah.
Well, then we turned it into if then else.
Yeah.
But at the hardware level, I mean, we start at the very fundamental level of NANDs and ANDs and NORs and things like that.
Yeah.
We don't have that in quantum computers.
Okay.
We have other things instead.
Okay.
And so the idea is, okay, you have to learn what those things mean and what they do. And then once you begin to understand that, then you can start to think about the problem domains that potentially this can solve, which are outside the problem domains that classical computers will ever solve, no matter how big they get.
Just because of superposition.
And entanglement.
Yeah.
Well, what are some? Can you speculate about what are some of the applications that quantum computing will enable?
Yeah, great question. So early on, we see commercial value coming from chemistry-related problems. One of the things that we did at IBM Research last fall is we published in Nature an article. It was actually on the cover of Nature. It was an article about building a quantum mechanical model to represent a molecule. Where we calculated the energy states. So we used qubits to represent electrons, and we made the computations from there. Why is this significant? Because on a classical computer, you can't even do this for something as simple as a water molecule. We did for instance, a caffeine molecule on a 16-qubit machine. And now we're talking about things as big as 50.
Yeah. You're talking advanced science experiments and data analysis on a whole new technological level.
Right. So out of these types of chemistry problems, we foresee advances in material discovery, drug discovery.
So are you talking like super advanced superconductive material discovery? That kind of stuff, like
that
increasing the superconductivity to thus
could be that. There's a lot of different areas in terms of material discovery that could benefit from
plastics.
this. Absolutely, polymers, solid-state electrolytes, and many things. Yeah.
See, but when I look at this, I think about like pictures we've seen from like 1950 IBM punch cards in like a room filled with spinning tapes or whatever. And I'm sure if I asked the IBM guy in 1950, will I ever be able to stick this computer in my pocket? They'd be like, hell no. So, I mean, the question really is, what sort of application for the average person, like I don't need to discover caffeine molecule other than a cup of coffee. What will this do? Will this be artificial intelligence? Will this be...
Yeah, good question. So as we continue to scale these machines up, we see problems in other areas such as optimization, such as machine learning, which has to do
like
with
Watson?
the artificial intelligence world, right? And certainly Watson figures into that picture as well. Big data search, there's some very difficult problems with big data search that quantum computers offer a lot of hope for. And then what's been widely published, of course, is cryptography. And we certainly see that there
Cryptography, so like cryptocurrency?
encryption. So encryption can be used for a number of different things.
Could you use it to...
Encoding and encryption.
Could you use it to solve for bitcoins and mine for bitcoins and stuff like that?
Yeah, great question. So eventually, when these machines get to the right scale, we will
pay
be
for that
able
somehow.
we will be able to do, first off, encryption that truly is secure. There absolutely is no way that you can break the encryption.
What about 51 qubits?
Well, no, it'd be,
It's not based on that.
Doesn't
what
work
I've
like
seen, it
that.
would be like a combination of sound, image, character. It would be like a combination of all inputs that could be gathered to create an encryption for a quantum system.
That's true. That could be something like that. So one is creating the encryption, and then the other aspect, which a lot of people are asking about, I don't know, they must not have the same ethics as me, but they ask about breaking encryption. And yes, these machines offer the potential to be able to break encryption
Existing
of
encryption.
any classical computing-based encryption.
Because it's just that much stronger.
Correct. Remember, the power is that I can consider all these states in a single operation. So like in the case of 50 qubits, 2 to the 50th power, that's what we're talking about. So
Simultaneous state machine, like where all states can happen at one time.
yeah, there you go. There
Okay,
you go.
I'm getting what you're saying.
Right. So a very simple example that a lot of people can get their heads around is the traveling salesman problem, where the salesman needs to go to different cities and you want to calculate the optimal route.
Yeah. He would have
in-
to have simultaneous states to be able
Yes,
to calculate that efficiently.
Right. So in the classical computing world, we do that through an iterative technique, right?
One step at a time.
And when that problem gets big, we don't solve it, right? But in a quantum computer, we can consider all the possibilities at once.
Yeah, all the states, all the ins and outs,
Yeah.
everything. That's cool. So then on the chip, when you're calling into the qubit and you provide, like, let's say you provide power and supercooling to the chip, do the qubits just appear like they were always there? You just have to reach the right temperature and state to have access to them? Or is it something that's produced like when you turn the power on and because of its certain conditions, the qubit is present?
Yeah, we have to get it to the right environmental conditions and so forth
For it to
in
appear,
order
essentially.
for the quantum characteristics to exist.
Wow.
So,
That's
but
amazing.
once we reach that, it's actually can be very, very stable.
Yeah,
For
it's there.
instance,
Once you reach like the right rotation and everything and the right temperature. And
Right. So for instance, I mentioned we have IBM Q experience, which is the publicly accessible, free access to IBM computer. That quantum computer, that machine we had up running for a year and a half uninterrupted. So I would say that's pretty stable, right?
So when
especially at a superconductive state.
we got to get back to the question of A, why does it look like a 1950s science fiction movie? And B, how do you, where does a monitor plug in? How do you interface with this as a human?
Yeah, great questions. So I like the first part of it because it's somewhat accurate.
Yeah.
In many ways, we are like back in the 1950s because all of this, a lot of what we do with classical computing doesn't apply here. So we have to recreate a lot of the infrastructure and so forth. Now, hopefully, we're a lot better at it this time around. We can go a lot faster. We
Right.
learn from all of that, right?
Right.
Right. So, but absolutely, it does have that look. And
Wires
feel to
hanging
it.
out and everything.
Yeah. So, does have that feel to it. I agree with you, and it will continue to evolve as the science progresses here. What was your second question?
Well, I don't see where a monitor plugs in. Like, how do you interface
so
with
the
it?
interface model is actually through the cloud. So
Does it have an Ethernet port or a Wi-Fi connection?
So what happens is this connects to a whole bunch of electronics infrastructure, which you would see over in the video.
Like the terminal server.
That we can then turn, we can then turn this into information that we're normally used to working with in the classical world, and then we can get that back to people or to this from people over the cloud.
So it's very similar to like an old mainframe terminal service type of environment where you connect into it almost like your signal processor, and then your terminal depicts what the graphical representation is based on the response from the service.
Yeah, funny how things go around, huh?
Hey, we're back in terminal days.
But I mean, is there an OS for it? It's not like you're going to have like Windows running on your quantum computer, right?
Right. So we have we've written a assembly language for quantum computing. We call it Quasm. So it takes advantage of those fundamental building blocks, similar to like and NOR gates, things like that.
So you take the Q logic set essentially and put it into like an assembler type language.
Right, right. And then we can move a level up to that and use something like Python and Jupyter notebooks to be able to create things of real significance.
How's the Corlet language? And I know you guys are working on like a neural processor that works with the Corlet. Is that going to be integrated into the platform?
The what?
The Corlet language that IBM is working on? Be familiar on that level. It's kind of very similar to Python. It's like a neural processing language that's being worked on.
Yeah, at this point, I mean, all of that can be possible.
But it's pretty much Python though, right now. Python
right. Right now, we've chosen to make use of Python. What happens is at the lower stages here, like of course the assembly language has to be very specific. As we move up into the higher and higher levels, now we have opportunity to make some choices. Right?
So right now it's pretty much is like Python's your interfacing language, and then whatever other language libraries that come besides the Python.
Right.
Yeah, because a lot of the IBM stuff, I talk a lot with it. A lot of it, I was wondering why a lot of it was written in Python.
Yeah.
I was like, what are they doing with all this Python?
Yeah, we of course, this is still in IBM research. So in IBM research, we take advantage of kind of whatever is most available and our researchers are most comfortable to use. And then as we turn it into a business and a product, then we make product decisions.
Yeah, and you create the libraries and the interfaces. And
right. So next year we're expecting this to transition into our IBM Systems business unit. We're going to.
So it's going into the Watson services then?
No, it's going into the IBM Systems business unit.
So you'll be able to buy one?
By processing time.
Probably, yeah. Instead, what you want to do, we're envisioning a shared access model because these are very expensive to build. So we expect that people would prefer that kind of shared access. Also, the environment, the support, all of that stuff around that is non-trivial. So we're going to do this in Poughkeepsie. That's one of the locations, IBM Systems, where we build mainframes. People who buy System Zs will have the option to be able to pick up, shall we say, quantum accelerators.
Quantum accelerators?
Yeah.
Wow, that sounds imaginative. Wow.
I still have no idea what the hell it's doing.
I'm peeking like
Dan. I mean, it's really great of you to
and their interactions on the 5 gigahertz band, and then he says quantum accelerator, and I'm like, I totally get what you're saying.
Well, good. I'm glad that you do because I certainly don't. So, is there anything else that we want to ask, Quinn?
No, actually, you were really helpful.
Yeah, we really appreciate it, Dan.
I mean,
Thank you very much.
On the 5 gigahertz band, that's been really in my research. That's been like really difficult to understand the interfacing of that qubit to the machine if it's not being done through wiring or a hard coded type of way. How is it communicating if it's doing it through the 5 gigahertz band? That opens up a whole spectrum of understanding to me now that I know how the qubit and you're reaching into it through the 5 gigahertz and yeah,
but
closes a lot of gaps.
In your wildest imagination, there's no day where you'll have like a little kegulator sitting next to your desk to refrigerate your home quantum computer, and
it won't be during my working career. We're a long ways away from that. Yeah.
seems like the whole Moore's law on processors has slowed down. There's no processor faster than 4 gigahertz. I thought we'd been at 8, 16, 32. This is not the next wave of that?
So in the quantum world, it's not about clock speed. It's really about qubits, and it's about preserving the quantum characteristics, particularly superposition and entanglement. So here, the clock speed is more important to make sure that you can do something with that quantum information within the coherence time. Coherence is the idea of how long does that quantum information stick around, right? So that's the challenge of building quantum computers. Can you preserve the quantum effects? Can you take advantage of the quantum effects? Can you see those in your computer? B, do you have coherence time that's long enough to be able to do something meaningful? And C, can you scale this such that you can start building larger machines?
And once it scales up, you'll scale it back down to the individual, but we're not at the scale up factor yet.
Sure.
I just thought of another important question. So you're talking about the qubits, and those relate to the binary ones and zeros that a traditional computer processes, which is really the information. But we haven't spoken at all about a CPU. Is there a CPU in a quantum computer?
Yeah, it's basically built into the qubit structure, shall we say. So how the qubits are architected together includes
like each one is an individual.
Yeah, it's like the computational capabilities right on board there. It's kind of, if you think about the AI world, people were using GPUs because they were particularly well suited for the type of computation that you're trying to do.
For artificial intelligence?
Right, right. So in many respects, I see a parallel here in that here's an architecture that is particularly well suited for being able to work with the quantum information. That's what we're trying to do.
Wow.
It's pretty cool.
Yeah, thanks for your time, Dan. We really appreciate that.
You're welcome.
IBM Quantum Computing here at CES 2018 with Dan from IBM and Quinn. Wow, I still have no idea what the hell you just told us. Yeah, that's great. Thank you very much, Dan.
Really appreciate it.
And you can see this video on YouTube at Crowdsource the Truth.
Okay.
Really
great.
appreciate your time.
Send me a link, please.
Yeah, we will. We will.
All right.
Thank you, sir.
Yep. Bye-bye.
So Quinn, do you know more about quantum computing now? I bet you do.
He helped me connect a lot of dots on the communication spectrum for him. So now a lot of the work that I'm doing makes total sense on things that could be happening in a 5 gigahertz band, like communications.
People are going to hear 5 gigahertz and they're going to think 5G network. Is that the same thing?
Probably very close.
Okay, and then also...
I can't say for sure, but I'm saying it's probably pretty closely related in some way.
Don't you think it's interesting that he was talking about GPUs and artificial intelligence? Who else was talking about that? We were talking mostly about cryptocurrency mining, but massive networks of GPUs seem
useful.
How do you like that guy's hat?
That's the superposition right there, man. You
okay.
Have the superposition.
All right, Quinn. I think that's it. We're not going to find Sophia, but we did learn a lot about quantum computing. I hope that people. Let me make sure this stream is still going.
I think it is.
Yep, it is. All right, everybody, I hope you enjoyed that little lesson. Yeah, cloud processing. Black goo is the God particle, someone says.
Black goo is the God particle.
Unbelievable. All right.
Unbelievable. Mind blown, right?
Thanks for watching, everybody. We'll be back later.